Hi, I'm Abhinav Khandala, and I'm a principal research scientist at IBM. I'm very interested in helping build better quantum computers and figuring out what one can do with them. Today, I'll be telling you about accurate quantum computing in the utility era, and maybe two words to emphasize here that will be recurring themes in this talk: uh, accurate and utility. But perhaps before we dive into that, maybe we can start with a question that I used to often ask myself growing up. Do we really need faster computers? I would keep hearing about these new generations of Pentium processors. Perhaps there would be a new computer come in someday at home. And for the usual tasks that I was trying to do, perhaps stream some videos or send some emails, there wasn't really a dramatic change in my ability to perform those tasks. Right. So it's worth asking, why do we even need to build faster computers? Why do we even need to build better computers? In the context of quantum computing, perhaps you've heard that these machines can possibly do things that our regular classical computers cannot do. But also, if we now look back, many of the incredible things we've been able to have, the incredible technologies we've been able to build access towards, be it smartphones, things like ChatGPT. We probably wouldn't have had access to these if, as a civilization, we didn't have almost this maniacal obsession over decades to build increasingly powerful machines, increasingly powerful computing machines, even before we knew what we could do with them. Right? So in that context, I'm certainly very much a believer in build it and they'll come. We build increasingly powerful machines. We figure out how to use them, and as a civilization, we're capable of figuring out what are the kind of applications and tasks one can perform with these increasingly powerful computers. Right. So one example of problems that our regular classical computers often struggle with is the problem of electronic structure. Okay, so you might have seen curves like this in perhaps high school or college. These are traces that try and describe how the potential energy of, say, a diatomic molecule changes as you vary the separation between two atoms. Okay, so when these two atoms are very close to each other, you have a state of high energy. This is an unstable configuration. If you completely took them apart, well, now these two atoms are dissociated, and you're in a state of no interaction between these atoms. Now there'll be this very special distance, and this is called the bond distance. And when the separation between the atoms is at this particular distance, well, you're in the state of the least energy, and that's the equilibrium configuration. Okay. Now, the amount of energy it takes to now break this bond is basically the dissociation energy. And this is actually a very, very important quantity because chemical reaction rates are exponentially sensitive to the accuracy with which one can calculate or estimate or measure this dissociation energy. Okay, so well, how does one actually have access to this? Right, very often one might have to do an experiment, but if that's not immediately viable, one has to run a simulation. One has to do a calculation. Fortunately, we have the equations that we need to solve. It just turns out that solving them is a very challenging task. This is typically an eigenvalue problem where one has a Hamiltonian that describes the system, and we're tasked with trying to access the lowest energy state, the ground state, and get an estimate of the ground state energy. Okay, so typically what this task reduces to is you have a matrix representation like this of the Hamiltonian, and you have to perform a diagonalization. Okay, if one had n spin orbitals, this basically means you're describing your state by a matrix with 2 to the n entries, and now trying to store this many numbers and manipulating them and so on, this can be a very expensive task. Once you're even at the level of 55 to 60 spins, perhaps, storing this exceeds memory on perhaps the most powerful supercomputers that we have at Oak Ridge National Lab, right? So this is a challenge. This kind of exact diagonalization becomes a very challenging task once we go beyond a particular scale. And this is not a problem that we just discovered. This was a problem that was quite known even from the very initial days of quantum mechanics, right? Dirac pointed out, way back in 1929 that the underlying physical laws necessary for the mathematical theory of a large part of physics are known. But the difficulty is that the exact application of these laws leads to equations that are much too complicated to be soluble. Okay? So even though we're able to express the equations that we need to solve, performing an exact diagonalization to access the quantities we're interested in, that becomes a very challenging task. Okay? And therefore, it becomes desirable that approximate practical methods should be developed. And this is basically what's driven a lot of innovation. A big reason for us being able to simulate so many different materials and for many different applications today is because we've developed approximate classical methods that seem to work quite well. Okay. Now, the question though is, if you cannot solve a problem exactly and you don't have access to the exact answer, and all you can rely on are these classical approximations, how do you build trust in these methods? This is basically a game that computational scientists working with classical methods have been playing for decades. This is essentially what they work on, right? So there are perhaps a few different things that one can do to try and build trust in these approximate methods. One, you could first operate at small system sizes where one can do an exact diagonalization. Okay, and now you have the answer there, and you can benchmark the performance of your approximate method at those scales. Perhaps even at larger scales, even though one might not be able to do an exact diagonalization in general, there might be special points where one has analytical solutions. One could benchmark these classical approximations at those special points. Okay, and then, of course, there's going to be a host of literature on other classical methods, well-established classical methods. And when you develop a new algorithm or a new method, perhaps you can compare to the performance of those well-established methods and perhaps build trust that way. Okay. The other common game to play is to systematically increase some computational resource, the amount of memory, the amount of runtime, and then see if as you increase this computational resource, your results tend to converge towards some value. And perhaps that gives you confidence that maybe your simulation, your approximate simulation is doing a fairly good job. There is, of course, no guarantee, but even in the absence of an exact result, this is the game that classical computational scientists have been playing for decades, of using approximations and trying to build trust. So the question then is, when can we play, or how can we now play this game with a quantum computer? Okay, so there are two ingredients, and one can directly see this from the evolution of classical approximations. One, you need to be at this scale that's beyond exact diagonalization. And throughout this talk, I might switch between the phrase exact or brute force classical simulation, exact diagonalization or brute force classical simulation. I typically mean the same thing. So you need the devices to be at least at a scale that's beyond what one can do with brute force classical simulation. And then two, you need the quantum computer to produce trustworthy solutions. Okay? So, well, on the second point, the challenge is if we compare classical computers to quantum computers, we compare the error rates on the fundamental building blocks, right? Currently, the errors on quantum computers are perhaps 23 to 24 orders of magnitude more error prone than the basic bits that one has in a classical computer, the transistors. Okay, and so when the error rates are this dramatically high, can one build trust, or can one hope to access trustworthy solutions from a quantum device? So this was always a known challenge. And then there is a long-term solution to this. And perhaps you've already heard about quantum error correction and how this is going to work around this problem. Okay? But we can change this question now to, can current devices, pre-fault tolerant quantum computers, already produce trustworthy solutions? Okay? So to build some intuition towards this, let's try and work through a very simple example. Okay? Let's assume that I had a quantum circuit where I had 100 qubits, and I'm trying to execute, say, 10,000 2-qubit operations, 2-qubit entangling gates. And each of these gates has a fidelity of about 99.9%. That's a measure of how accurately I can execute that gate. Okay? So if I had 10,000 of these, the fidelity of the state I prepare at the end, so a measure of the overlap of that final state with the ideal state that I should have prepared, is going to be a very low number, about 5e minus 4. Okay? So this is a challenge, right? These state fidelities are going to be very low in the absence of fault tolerance, in the absence of significantly better error rates. Okay, let's now walk through another example. Let's assume that I had about 1,000 spins all aligned in the same direction. Okay? If I now look at the average magnetization of the system, it's 1. They're all aligned in the same direction. And if I flip one of these and I look at the overlap between the two, the fidelity is going to be 0. But if I now ask again the question, what is the average magnetization? Now that's going to be incorrect only in the third digit. You get a value of 0.998. So perhaps that gives us hope that even though the fidelity might be very low, okay, there might be quantities like this average magnetization here. There might be certain observables that we have access to that are perhaps not as sensitive to noise and perhaps could deal with a little bit of noise. Okay, so let's run with this kind of intuition. So typically in a quantum circuit, we have a series of gates. The red blocks here represent the single qubit gates. The blue blocks represent the 2-qubit entangling gates. And we have a series of these. And we know that, well, in practice, when we try and execute a circuit like this on a quantum processor, you're going to have noise. So we're going to represent that by something fuzzy. And let's hope that if this circuit is a short depth circuit, which means that the number of these blue layers is not a very large number, perhaps we haven't accumulated too much noise. And perhaps if we haven't accumulated too much noise, the observable we tried to measure at the end of the circuit, very much like the average magnetization that we had in the previous example, perhaps that isn't too corrupted. Okay, so perhaps even though one has a noisy quantum processor, a pre-fault tolerant quantum processor, one could maybe execute a short depth circuit which hasn't accumulated too much noise and measure quantities, observables like that average magnetization. Okay, so this was something we tried way back in 2017. Okay, and we're going to get back to these kinds of traces that we saw on one of those initial slides. This was a molecular simulation that was attempted on a superconducting quantum processor to simulate the energies of lithium hydride using about just 4 qubits. Okay, and even at this very small scale, what you actually saw here, that the energies were fairly atrocious, for lack of a better phrase, right? Particularly if you asked a quantum chemist if they would care about errors at this scale, and this goes way beyond the kind of accuracies a chemist would be interested in, particularly because those chemical reaction rates are exponentially sensitive to the dissociation energy. Okay, so even at this very small scale, running a short depth quantum circuit and trying to measure the energies of some very small molecules led to very large energies, led to very large errors. Okay, so the question is, well, is there any hope, before fault tolerance? Is there a way to actually improve some of these estimations? And this question basically led to the invention at IBM of methods that we refer to as error mitigation. Okay, it was also simultaneous work from Simon Benjamin's group at Oxford. And the basic idea with these methods is that, well, one, you want to first characterize the noise in your device. Okay. And once you have a fairly representative model of that noise, you want to manipulate it in very controlled ways. And then you want to undo its effect. Okay. Now, this isn't something that's a completely alien concept, right? Even in our day-to-day devices, our noise-canceling headphones, our cell phones, they all use some principles of noise manipulation to undo its effect, right? So that's the basic idea. And to give you an example of one of these methods called zero noise extrapolation, I'm going to talk you through some example where, without going into too many details, I'm just going to tell you that the expectation value should have been 1. Okay? That's what the ideal result should have been. We run the noisy quantum circuit, okay, at this base noise level of 1, and you get this green circle. That's the data point. And as you can see here, there is going to be some bias, some error when you compare to the ideal result. Okay. Now, if you had a model of the noise and you were able to manipulate it precisely, let's talk about, in this example, manipulating it in a way where you have precisely amplified that noise by a factor of 1.2 here and 1.6, you end up with even more noise in the circuit, and that leads to even more error in your expectation values. Okay. Now, by combining these expectation values at these 3 different gain values and trying to extrapolate to the zero noise limit, you actually see that you can produce a result that's very close to the ideal. Okay. So this is an example of how one could characterize the noise, precisely amplify it, remeasure that quantity of interest at a few different noise amplification or noise gain factors, and then use that information to infer or estimate what that expectation value was in the absence of noise. Okay, so this was basically now a technique that we used to revisit that lithium hydride simulation using 4 qubits. Okay, so 2 years later, we tried to repeat the same experiment, and lo and behold, we have a much better result. These white points from the quantum computer show much better agreement with the ideal trace. Okay, the challenge though here is that this was just a 4-qubit simulation, right? These are problems at a scale that one could have simply diagonalized, perhaps even on your smartphone. So this raises the question, well, what are the criteria that we need to satisfy for a quantum computer to have utility, right? So 1, you need the qubit counts to be at a scale that's beyond what one can do with exact diagonalization or brute force classical simulation. If not, one would just use a classical computer. There's no need to use the quantum computer, right? And the second question is, even at the scale, even when you're operating at a scale that's beyond the scale of where one can do a brute force classical simulation, you need the quantum computer to produce trustworthy solutions. And once you have that, then you can begin to play the game that computational scientists have really been playing for decades with classical approximations. Okay? So, on point number 1, well, at IBM, we've been building increasingly larger processors. In 2023, for instance, we built devices with over 1,000 qubits. But already at the 65 qubit to the 100 qubit level, perhaps already we're at the scale where we're already beyond what one can do with brute force classical simulation. Okay, so the second question then remains is we have devices, we have quantum processors that are at these scales that are beyond brute force. Can we still use methods like error mitigation on these large scale devices to produce trustworthy solutions? Okay, so, and with that, I'm going to describe to you now an experiment that we published in 2023. This is called the quantum utility experiment. So this was an experiment on a device with 127 qubits. And here, basically, we have a network of qubits. We're going to map an interacting spin system, a network of spins, onto this network of qubits. And then we're trying to ask the question, how does the magnetization of this interacting spin system evolve as I have an external magnetic field kick. So if I keep introducing kicks with an external field, how does this interacting spin system behave? How does that evolve in time? That's the question we're trying to ask. Okay, and we can study the evolution of this magnetization in time. Perhaps we can also study the evolution of this magnetization as we change, say, the angle of this external field kick. Okay, so let's focus on that example right now. This was mapping this problem onto a quantum circuit is something one can do with the circuit we used was using all 127 qubits and going up to 15 entangling layers. Okay, so this was basically looking at what that net magnetization was and how that was evolving as we changed the angle of that external field kick, right? Now, in the absence of any error mitigation, we get this green trace, and then we remeasured these expectation values at different noise levels, and we tried to do an extrapolation, and we now get the blue trace. Okay. Now, this is a problem at 127 qubits. This is clearly at a scale that's well beyond what one can do with brute force classical simulation. And we didn't know if this was producing any meaningful results. So we approached some experts at the University of California, Berkeley, Professor Mike Zelatel's group and his graduate student, Sajant Anand. And we asked them to help us benchmark the performance of this experiment, right? So we didn't have access to the exact solution to begin with. And Mike and his group are have developed their expertise with classical approximate methods, and so we tried to compare the performance of the quantum experiment with some of those classical simulation methods, right? And what you see is, well, to begin with, you have fairly good agreement between at least one of these classical approximations and the experimental methods, and then as the experiment begins to get a little more complicated, as the entanglement growth in the circuit increased, you begin to see these deviations between the quantum experiment and these classical simulation methods, right? And all our immediate reactions were that surely the quantum experiment was wrong. The experiment, the circuits are getting more complicated, so perhaps you're more sensitive to noise, and the experiment must be wrong. Thankfully, our collaborators persevered. Andrew Eddins and Sajant thought about this a little more, and what they pointed out was that we were looking at local observables, just individual magnetizations of spins, and the circuit depths were not too deep. These were just 15 entangling layers. So if you try and trace back all the gates that play a role in the accuracy of estimating every individual magnetization, well, the number of qubits that play a role actually is not that large. So this is basically trying to draw out a light cone of influence. Okay, so where all the gates in the quantum circuit that lie within the light cone could have an impact on the observable you care about, but the vast majority of the rest of the circuit might not. Okay, so because the number of qubits are now a much smaller number in the light cone compared to the full 127, it is now possible to do an exact diagonalization, for instance. And then with that trick, Sajant was able to produce now an exact trace, okay, of what the ideal result is. And we were pretty amazed to see that the quantum computer with error mitigation actually is producing results that really match up well to the ideal result. So this really gave us a lot of trust in our device and the methods. Okay, so with that, we then decided to go even beyond what one can do with this exact verification. Go to circuit depths where one can't play this game with light cone reductions, where we didn't have access to an exact solution anymore. Okay, so this was an experiment we also ran, and we published the data, and then a number of classical simulation groups tried to benchmark the performance of the experiment, right? And I have many of these described in these black boxes. And if you want to look at many of these results, you have about a variation between all of these, and that variation goes up to, maybe say even 20% at this pi over 4 angle. This is exactly the game that people have been playing with classical computation, right? Where you don't have an exact solution, you only have access to approximate methods, and you have to compare how one approximation compares to the other and try and get some sense of trust, right? And that's the variation between all these different methods. Now, what I haven't told you is within this variation lies points that were from an IBM quantum computer with error mitigation, right? So what this means is basically now with a quantum computer at this scale beyond brute force classical simulation, a scale we refer to as the utility scale, we are able to perform computations that we have trust in, that we can believe, right? And the level of accuracy compares to the kind of accuracies, the spread in a bunch of these other different classical approximate methods, right? So the basic takeaway from this experiment is that even in the absence of fault tolerance at scale, one can already use these quantum computers to produce trustworthy computations, which are at scales that are beyond what one can do with brute force classical simulation. Okay, so this was work from almost a couple years ago. I quickly want to give you a sense of what's happened since. Okay, as I kind of alluded to at the start, if you build it, they will come, right? Since this demonstration, there's been a dramatic increase in the adoption of at least the qubit scales for the kind of computations that are being run. And you'll see a number of different experiments now that are being run on our devices at the scale. This is just a small snapshot of many of the utility scale experiments. And people are continuing to explore what one can do with these devices and what kind of error mitigation methods, etc., one could use to actually get trustworthy solutions from these devices at non-trivial scales. Okay, so there have been many more utility scale demonstrations. We've also built much more reliable and faster software. It really amazes me that compared to back in 2023 when we first ran the utility experiment, if you try and rerun it right now, there's about a 75x speed up. So experiments that took about 5 days are one can do in like a couple hours right now, and this is also very important for accelerating the discovery of quantum applications. The devices have improved. The quantum hardware is improved. We have about a 5x improvement in median 2-qubit error rates in our new architecture. The utility experiment was originally on an Eagle device. We now have Heron devices with a new architecture, a new coupler architecture that has much lower error rates. And this has a very important role to play in reducing the overheads for error mitigation. I also discussed with you that an important part of trying to use methods like error mitigation is characterizing the noise and then manipulating the noise to undo its effect. A relevant question in practice, though, is in the process of characterization and manipulation, is the noise drifting, right? And so methods to stabilize the noise become very important. And I'm just going to share a bunch of papers that refer to archive preprints if you're interested. But this has also been a very important addition to the hardware tools, right? And then people are continually developing more powerful methods of quantum information processing to use pre-fault tolerant devices, to use noisy devices and yet produce trustworthy, accurate solutions at non-trivial scales. So there's been a lot of interesting method development along this, and I strongly encourage you to take a look at some of these works. And then what's been a really interesting direction that's really developed over the last year or so is the direction of combining quantum plus classical in a framework that's referred to as quantum-centric supercomputing. So the question isn't of does quantum outperform classical or does classical outperform quantum? The question of can quantum and classical together perform tasks that quantum alone or classical alone could not have done, and building this muscle to execute novel algorithms and to solve problems that weren't believed to be accessible in the near term. There's been fascinating work down that path, but also then using some of these frameworks to develop error mitigation methods with lower overheads, combining quantum and classical. Right? And in this line, I just want to quickly flash some really fascinating work that I think you'll hear about a lot more in detail in perhaps the next lecture. Back in 2017, some of our first quantum chemistry simulations with those traces that I showed you at the start of this talk really went up to 4 or 6 qubits, and really the field was fairly stagnant there. Maybe there was a factor of 2 improvement in the scale of those kinds of experiments. And it really amazes me that now we're able to do quantum chemistry on utility scale quantum computers using up to even 77 qubits, are competing with state-of-the-art classical methods. And this is really a new paradigm where one can use quantum combined with classical HPC to execute problems that people perhaps didn't believe would be possible with quantum computing till one had fault tolerance. Okay, so with that, just my final take-home messages. Even with noisy quantum computers today, which are pre-fault tolerant, one can perform accurate computations at non-trivial scales, at scales beyond brute force classical simulation, beyond exact diagonalization. And we have these improvements in speed and the quality of our quantum systems, improvements in the hardware error rates. All of this combined with integration with classical HPC should very soon take us from utility to advantage. Thanks so much for your attention.